The complex form of the Fourier series is only done for periodic functions with period t, and it is given by that summation, where n starts from -infinity to infinity for the Fourier constant Cn multiplied by e to the power jn omega t. Now we need to recall that omega is equal to 2 pi f, which is in our case 2 pi divided by t. Remember, the frequency is equal to 1 over t, hence it is measured in per second. Therefore, omega has to be calculated for the complex form of the Fourier series, and Cn's can be found by using the formula 1 over t multiplied by the integral of f of t e to a negative jn omega t with respect to t. Note that we're integrating from the lower limit to the upper limit, and also the values for n are all integers. Let's do some examples. The first one is where we're given a piecewise defined function. The first interval is from -1 to 0, and the second interval is from 0 to 1. Note that that is how we write a periodic function, which represents that our period is 2. Hence, we wrote here t is equal to 2. And our function values are -1 between -1 and 0, and +1 between 0 and 1. And then one of the first things we do is to calculate the value of omega, and in our case, we're getting t. So we write down the formula as stipulated, the formula for the Fourier constants, because in order for us to do the Fourier expansion, we have to have that Fourier constant first. So substitute the value for t, substitute the lower limit and the upper limit. Note it's piecewise, so it's a sum of two integrals. So we integrate from -1 to 0 first for the function value -1, and note that we multiply by e to the negative jn, and the value for omega has been substituted there, is pi, and then we multiply that by t dt, plus the second integral based on the second interval from 0 to 1. And note the function value is +1 for the second interval. And then thereafter, integrate each term. The integral of the exponential function is the exponential function divided by the derivative of the power. Hence, we have here divided by -jn pi. And note, we have to stipulate the interval of integration between -1 and 0 for the first one, and 0 and 1 for the second one. Note, because both of them have got n in the denominator, we have to stipulate that n cannot be equal to 0. And then thereafter substitute the limits. Recall that when we substitute the limits, we start with the upper limit first minus the substitution of the lower limit. So we have e to the power 0. Note that that negative is still there, and the negative in the denominator, I've left it there deliberately. So substitute the limits, e to the power 0, because in place of t we substitute 0, so we'll have e to the power 0 there, minus the substitution of the lower limit, which is -1 in place of t, changing that whole power of e to be positive, jn pi. Plus, now we go to the second term. We do the same. Substitute the upper limit, which is 1 first. So we have e to the negative jn pi minus the substitution of t equal to 0 for the second part. And then Note that we still have that n not equal to 0. We can't leave it because we still have n's in the denominator. And then we have to remember that e to the power j n pi and e to the power negative j n pi are both equal to negative 1 to the power n. Reason being, e to the power j n pi, when n is 0, we will have cos 0 plus j sine 0, which is going to be 1. When n is 1, you'll have cos pi plus j sine pi, and sine pi is 0 and cos pi is negative 1. So we have 1, negative 1, 1, negative 1 as our answers for both e to the power j n pi and e to the power negative j n pi. Hence, we have to substitute negative 1 all to the power n, and then thereafter simplify. Note that these two terms become 2j over n pi into minus 1 to the power n, and the first and the last term also can be combined to form negative 2j over n pi. Remember, e to the power 0 is 1. Combining these, that's the step that I was talking about, and then we take 2 out, cancelling that half. Then that's the formula for our Cn. Then, because this one is for n not equal to 0, we have to calculate C naught. We go back to the formula and make sure that the power of E is 0, and then we substitute. Our f of t is minus 1 between negative 1 and 0, and positive 1 between 0 and 1. Then we do the integration. We'll get negative t in the first one and positive t in the last one. But remember, the limits are not the same. Substitute the upper limit first minus the lower limit, and substitute the upper limit first and then the lower limit last. And please check to see whether one is the correct answer. And then we go to the formula for this series. It's C naught plus the summation of Cn times e to the power j n pi t. And note that we have to specify that in the summation, n is not equal to 0 because we have C naught outside the summation sign. Cn, we take it down as it is and we substitute it in there. Note that you must remember, in place of omega, substitute pi. Then we go to number 2. We have been given f of t equal to 2t, and the interval is from 0 to 2. And again, our period is 2. So that means, again, omega is going to be pi. So we substitute the period, substitute the interval, substitute the function multiplied by e to the power negative j n pi t dt. And then we took 2 out, so that's what we are left with. And then we use integration by parts. And we got those two terms. Please confirm that those are the two terms that we got are correct, and note the limits. Both terms have got the same limit. They are unlike the first example, which was piecewise with 2 different intervals. Here there is only 1 interval. And then note that we have to specify n is not equal to 0 because we've got n in the denominator in both terms. Substitute the limits, and that's what I got. Please check whether I got everything right. So the next step is to move j from the denominators up, remove the brackets in those denominators that have got squared, and also substitute for e to the power negative j to n pi. So I've got 2j over n pi, because e to the power negative j n to n pi is 1. So we have 1 there. So and 1 over negative j is equal to j. So it's 2 over n pi multiplied by j. The next term, we have 1 in place of that exponential function, and then plus the last term. And then those two, they cancel each other out, leaving us with 2j over n pi, not with n not equal to 0. And then we have to calculate C naught yet again, and please confirm that the answer for C naught is 2. And then we substitute Cn into the summation multiplied by e to the power j n pi t for n not equal to 0, and C naught equal to 2. Okay, here are some exercises. Number 1, we are just confirming the answer has been given, confirming the interval is minus pi and pi, and the period is 2 pi. 2b, I would rather we change sine half t to exponential form. Remember, sine z is equal to e to the power jz minus e to the power negative jz, all divided by 2j. I believe that it would work better than using sine half t and having to do integration by parts. Also with 2c will work. Then moving forward, we have the multiplication principle. Note that we have two functions that have the same period, which is t. Then they can be represented in that format using the multiplication principle. Note that when we use the multiplication principle, we simplify the left-hand side as well as the right-hand side. Note also that dn star represents the complex conjugate of that Fourier constant. Cn is a Fourier constant for f, and dn Fourier constant for g. Parseval's theorem works also the same way as the multiplication principle, but now there are not two functions but one. So on the left hand side of the multiplication principle, we have f of t multiplying f of t. That is why we have f of t all squared. And here on the right hand side, you have, instead of c naught times d naught star, you have c naught times c naught star, and also cn times cn star. That means in place of dn star, you have cn star. That is the complex conjugate of cn. Once again, you have to simplify fully. So if the Fourier constant has n in the denominator, then it means you have to have c naught. Thus, we say that we have a root mean square represented by either the right-hand side of the Parseval's theorem or the left-hand side of the Parseval's theorem. So if you've been given the functions only, you use the right-hand side with their period. And if you've been given the constants, then you use the right-hand side. That is the constant side. Then we go to the power spectrum. The average power associated with a periodic signal is defined by the mean square value, and we take the left-hand side of Parseval's theorem if you have been given the signal itself. But if you've been given the Fourier constants, then we can use the right-hand side. Here are some examples that you can use to practice on finding the complex Fourier series as well as the power spectrum. But for this one, we were asked to find the power spectrum, and because the Fourier series has been given to us, then all we needed to do was to do this, the absolute value of Cn squared, and that's what we got as an answer. Now moving quickly to the Fourier transform. Now the Fourier transform is used for non-periodic functions or non-periodic signals to provide a gateway from the time domain to the frequency domain. And if that integral exists, it gives us the Fourier transform. Note that we have no period there because we are dealing with non-periodic signals or non-periodic functions. So we have the integral from minus infinity to infinity, f of t e to the power negative j omega t dt. And therefore it's Fourier, it's known as the Fourier transform. Note that the Fourier transform symbol is f of j omega. So that means all the answers that we get are a function of j omega. If we want now to reverse the process, we find the inverse Fourier transform, which is f of t, and then it is given by 1 over 2 pi multiplied by the integral of the Fourier transform multiplied by e to the power j omega t. And note that we are integrating with respect to omega from negative infinity to positive infinity. As stated, we have a time domain and a frequency domain pathway that is represented by the pair Fourier transform and its inverse. Now let's quickly do some examples. Given f of t equal to h of t times e to the power negative at with a greater than or equal to 0, we're asked to find the Fourier transform. So the Fourier transform, remember the formula, it's f of t multiplied by e to the power negative j omega t dt. And then because these two are exponential functions, we add them up, taking negative t out, and then use now the Heaviside function to change the limits. Remember, the Heaviside function is 1 for t greater than or equal to 0 and 0 for t less than 0. So we have 1 multiplied by that exponential function, and the limit now changes to 0 up to infinity, and then we integrate. After integrating, we make use of our limits. Remember that the integral, the limit of e to the power negative t approaches 0 as t approaches infinity. Hence, you'll have 0 minus e to the power 0. Hence, we have that answer for this integral. Going to number 2, determining the Fourier transform of a rectangular pulse as given in the diagram. Note that the function value is a and t is between negative t and positive t, and it is included, so we have the absolute value of t less than or equal to capital letter T, and it's 0 everywhere else. So the first thing we ought to do is to write the rectangular pulse in mathematical format. That's the first step. And then find the Fourier transform of our f of t. And our the function value of our f of t is a. That is why we've got a there. And the interval is not now negative infinity to infinity because it has been given. It's from negative t to t. And then we do our integration, take the limits. Now we need to also recognize that e to the power j omega minus e to the power negative j omega t represents a sine function. So we have to change to a sine function. Therefore, sine of omega t is supposed to be e to the power j omega t minus e to the power negative j omega t, all divided by 2j. And therefore, because of that, we change the exponential part of our Fourier transform to 2j sine omega t. Now, because we have a sine function there, we need to remember the special functions that we were introduced to earlier on in our course. That sinc function of omega t will be sine omega t over omega t when omega is not 0 and 1 when omega is equal to 0. Therefore, the Fourier transform of our function changes then, because we have the negative ja over omega. We don't have omega t in the denominator. We introduce t over t so that we have sine omega t divided by omega t. And because of that, we do have 2at sinc omega t when omega is not equal to 0. Then we have to find the function, the value for omega equal to 0. That is the Fourier transform. Then we go back to the integral of a with respect to time between negative t and t, and then we got the answer. Therefore, that rectangular pulse has got that Fourier transform for omega not equal to 0 and 2at for omega equal to 0. Please check all the steps and make sure that everything is in order. Number 3 is a piecewise defined function, and we recognize that we've got 0 for t less than negative 2 and 0 for t greater than positive 2. So therefore we have a sum of 3 integrals. So we recognize the intervals in each part of that piecewise function. We do the integration, substituting the limits. What I need you to do is to take this to the final answer. I would suggest that you take out 1 over j omega or negative 1 over j omega and then simplify. Combining the terms, that go together and check whether you're going to get the final answer. Then we move on to the inverse Fourier transform. We start with the recognition that we had pointed out, that we can go backwards from the Fourier. That means from the frequency domain back to the time domain. In the examples that have been given, we have to use partial fractions for number 1 and number 2, and also realize that number 3 we have a frequency shift, number 4 we have a time shift. So for the first two, it requires the factorization of that denominator and then taking partial fractions, and also recognizing that when you're substituting the values after taking the partial fractions, in order for you to get the constants A and B, we substitute the values for J omega. So please do the first two, factorizing the denominators, getting partial fractions, and then use the tables. Just make use of the tables to find the inverse Fourier transforms. Coming to the properties of the Fourier transform, all the transforms that we have been using so far, they have the linearity property, and we're going to use it just now. Time differentiation, we recognize that the first derivative gives us J omega multiplied by the Fourier transform of the original function. The second derivative, J omega all squared times the Fourier transform of the original function. The third derivative gives us J omega all to the power 3 of the Fourier transform. So let's do some examples making use of the linearity property and the time differentiation. Here is an example given that y j omega is equal to g j omega multiplied by u j omega, and we're asked to determine g of j omega from the differential equation. So what's the first thing we do? Find the Fourier transform of each term. Second derivative gives us j omega all squared times the Fourier transform of y. The first derivative of y gives us j omega times the Fourier transform of y, and note that we have that 3, which is a constant. We do the same with the third term on the left, and then the same on the right hand side, recognizing the derivative giving us j omega times our u of j omega, and the last one 2 times u of j omega. Take out y of j omega on the left and take out u of j omega on the right, and then thereafter divide throughout so that we get y of j omega equal to g j omega multiplied by u. Therefore, our g is the expression 3j omega plus 2 all divided by negative omega squared plus 3j omega plus 7. So as you notice that we've used both the linearity property and time differentiation property. Time shift, we have this recognition that when a signal has been shifted or say delayed, we are able to find the Fourier transform of the delayed signal, and it is given by e to the power negative j omega tau times the Fourier transform of the original signal. Now let's recall that the Fourier transform of our rectangular pulse was 2at sinc of omega t. Now we are asked to find the Fourier transform of g of t, which is definitely a delayed signal of f of t. By how many units? By t units. Hence we say that tau is equal to capital letter T, and we're supposed to substitute into that formula f of j omega is 2at sinc omega t, and into the exponent we substitute just the value of t, and that's it, and that's our solution. And then we have the frequency shift. The Fourier transform of e to the power j omega naught t times f of t is equal to f of j of omega minus omega naught. Let's quickly do an example. We are asked to find the frequency spectrum. Remember, the frequency spectrum is the Fourier transform of the given signal. So our signal has got cos of omega naught t. So the first thing we do is to change cos omega naught t, and we write it in exponential form, and then we'll have those two terms making use of the linearity property, and we know that according to the definition of the frequency shift, we're getting those two answers. Symmetry, energy spectrum, and power spectrum are given by those definitions that we can see. And I'm hoping that we're able to see for the energy spectrum and the power spectrum. It's slightly related to the energy spectrum and power spectrum for the power series, as well as for the Z transform.